My name is Andrew Keating, and this is my extra credit math project about the math behind synthesizers. It is commonly known that there is a mathematical relationship between notes. On the left image, we see notes that correspond to different fractions, and on the right, we see notes that correspond to different frequencies. In math, musical notes are represented through sinusoidal waveforms, and in music, we call these pure notes or fundamental notes or first harmonics. This is the mathematical equation that represents a pure musical note where capital P is the air pressure in decibels, A represents the amplitude, lowercase f defines the frequency or pitch in hertz, and lowercase t represents the time in seconds that the waveform lasts, and lowercase p defines the phase shift. And sometimes capital T is used instead of f, where t equals 1 over f and is known as the period. In this presentation, I'll be talking about different kinds of synthesizers. The analog synthesizer is what was used before computers were invented, so sort of the retro synthesizers. And an analog sound wave replicates the entire original sound. So here we see the sine graph of the original and the analog sound are identical. So here are the sine graphs of some different musical notes. And what we notice is the difference between notes are the frequency or period in math terms, and musicians refer to this difference as the pitch. Um, as you can see, the note A represents a sine of 880 hertz, and the sine of 1100 hertz represents C sharp, and the sine of 1320 represents E. A chord usually refers to a combination of different sound waves. And in order to get what that graph looks like mathematically, we just add the different sine wave functions. So we can see that on the right. And what's actually pretty cool is this guy named Fourier figured out that the combination of sound waves of any sound wave can be depicted by multiple sets of sine and cosine functions, which is called the Fourier series. Something that I use a lot are noise canceling headphones, and it was interesting to find out how noise canceling works. And the way that it essentially works is the noise canceling provides a phase shifted note to the note that you're hearing, and it essentially negates that note. So we can see the yellow graph is the first note, and the noise canceling represents that the red sine function in the rightmost picture. And on the bottom, we see how those two sine waves cancel each other out. So if you're an instrument player, like for example, I play the cello, when you play a note, you're actually hearing, there are actually multiple frequencies going on at the same time. While the fundamental frequency is what stands out, but there are also third harmonics, fifth harmonics, different harmonics um, that are positive integer multiples of the original frequency wave. So for an analog synthesizer, if you want to create these different waveforms, these different types of sounds, what you would have to do is add together different sine functions until you got the waveform that represented the sound that you wanted. So for example, on the top left, we have what is called a square wave. And in order to create that sound in an analog synthesizer, we can kind of see the evolution of that wave on the right side of it becoming from a sine wave to a square wave by adding multiple different sine waves together. So why use a digital synthesizer? Well, there are many benefits to using it. I personally use a digital synthesizer because it's much easier to use. It's versatile. You can create pretty much any type of sound that you want. Um, you can, you generate sounds that aren't heard in nature. You can create your own sounds. It offers a lot of sophisticated techniques that you can alter the different waveforms, different types of sound. Um, and you can just create music on, just using a computer. You don't have to record anything. And um, it's just, it's a universal instrument now, I think, in the modern age of music and technology. And you can also produce new instruments and resurrect old ones, so you can recreate that old retro sound. So here is a comparison, analog versus digital sound waves. So on the top, we see how the analog sound wave replicates the entire original sound, so the continuous flow of that sound, while a digital sound wave is only replicating like sampled sections. So you can get close to the original sound, but never the exact same organic sound. So this is a digital synthesizer that I've used called the Maelstrom, which essentially replicates digitally what a typical analog synthesizer would look like because we have these different knobs and sliders that do different things. And we have our frequency knob, which is going to change our pitch that we can modulate that. We have our different oscillators or filters, which essentially in a lot of digital synthesizers, let's say I want to combine a square wave with a sine wave, the different oscillators allow me to create both of those different waves and then switch between the two, so I can do really cool things with the sound. Another feature is the volume knobs, which can change the amplitude, and there's many other things. So a little bit more about how an electric oscillator works. It uses voltage from a power source to excite electrons, and it can produce sound by generating these periodic oscillating electron signals. So what an oscillator can do is it can control the pitch, and it can produce these different types of waveforms, the sine, squares, triangle, and sawtooth. So when you use an oscillator, essentially the original sound, the input signal, is always a sine wave. But what the oscillator can do is it can convert these waves into different waves. For example, a square wave, a sine to a square. If we select square wave on the oscillator, what the program does is it cuts off those top high and low ends to create that wave shape in that different sound. So from a more mathematical point of view, this is typically what an audio engineer would be looking at when they're analyzing different synthesizers and the way that they work in terms of their digital electronic components. And we have, I'm not going to get too much into this. We have uh, one is called uh, a ring oscillator and a gated ring oscillator. Um, and essentially what these do is they get the input signal and then the output signal that you can change the waveforms. Uh, so now we're going to get into what amplifiers are, and what they are is they control the volume. And here we have two graphs that show the difference in amplification. And here our equation P equals A sine 2 pi ft plus P. A represents amplitude. And in these graphs, we're looking at the note A. So the first graph, A is at 880 hertz, and in the second graph, A starts at 880 hertz and gradually gets louder as the amplitude increases to 1760 hertz. So here we're going to talk about frequency spectrum graphs, which are commonly built into a lot of music making software, so you can kind of visualize what's going on in terms of your different notes. So on the bottom left, we have our one singular note, and we see on the frequency spectrum graph that one spike, as opposed to a chord on the right, which is the three different notes combined together. So here are the frequencies of pianos and synthesizers. Here we can see the different frequency ranges. We have our sub monitors or our bass notes. And then we have our mid range, and then we have our high frequency notes. So here's the full orchestra frequency ranges. And we have our different sections represented in terms of the frequencies. So in the vocal section, we can see that the female vocals, our vocalists, have a higher frequency range than the males. Um, in our winds, we see that the flute is higher than the tuba, and so on and so forth. So different instruments can generate different sound wave combinations, and like we were talking about before, we have our fundamental sound wave that produces that singular sine wave, and then different instruments vary in their different harmonics. So we see how a violin, um, is much different than a trumpet, for example. But what a digital synthesizer can do is it can take something that was played by a violin and alter those harmonic frequencies so that it sounds like a trumpet, for example. So the way that digital synthesizers are able to alter these sounds is through what's called different or what called filters or modulators, which modifies the signal. Um, so in music, they modify the harmonic content of the signal, or what is called timbre, which is altering the characteristics of the sound. And filters also allow you to select a range of frequencies in a sound and then either amplify or reduce those frequencies. Um, so we have different types of filters. We have our high pass filter, which essentially blocks all the low frequencies, making a sound brighter. We have the low pass filter, which blocks the high frequencies, which makes it sound a little bit darker. And band pass filters, which can help create square, triangle, and sawtooth waves. So we're going to talk about some different waveforms that a digital synthesizer can create, and one of those waveforms is a sawtooth wave. As you can see, looking at the graph, it looks like a sawtooth, the waveform itself. And mathematically speaking, the amplitude in a sawtooth wave is equal to the inverse of its harmonic number. And when we listen to a sawtooth wave, it typically sounds like it has a buzzing characteristic to it, which is typically used in leads or melodies in electronic music. And looking at the graph that's on the bottom, we see that the more harmonics that are added in this manner, and this is looking at our frequency graphs, the more the wave will look like the idealized sawtooth wave. So another waveform that the digital synthesizer can produce is a square wave, which is typically heard in Nintendo games or early Nintendo games. Um, and looking at the frequency graph, the amplitude of a given harmonic in a square wave is equal to the inverse of its harmonic number, and we can see that there are not many divisions. It's not like the sawtooth wave. There are less. It's similar to what we would see in a chord. So another waveform is the triangle wave, um, where mathematically the amplitude of a given harmonic in a triangle wave is equal to the inverse square of its harmonic number. And looking at the graph, we can see it looks like a triangle, the different wave. And at the frequency graph below, we see that there's not many other frequencies. There's really predominantly that first frequency that is the most present. And comparing all the waves together, the sine wave is the most pure wave, the least amount of harmonics. And then we have the triangle wave, which has a little bit more than the sine wave, but not much. And then the square wave, which is more frequencies, and then the sawtooth, which is the most distorted, most fuzzy frequency. So here we're looking at two different graphs that represent um, the different instruments that you would use when you're composing or producing, and what their graphs look like. Typically, um, in the first graph, we have what usually would be like a bass. We want our bass to be pure. We don't want that many harmonics to interrupt that frequency because usually we don't want a really distorted bass. Um, so, typically we'll use, this sort of graph would represent something like a clarinet, for example, which has a very pure sound, or a bass that we want. And for our second graph, we're looking at a lead in electronic music, which is usually like a high. It dictates what the melody is. You're usually going to use a lead for whatever melody you're going to use, and this can, for people that don't know electronic music, it kind of resembles what a saxophone would sound like. We have multiple harmonic frequencies. Yeah. So I hope you enjoyed what I discovered about the math behind synthesizers, and hopefully you learned something from what I researched.